Hello everybody, I am Dr. Sergey Sargasov, actually a professor of mathematics, and I will my username is ponkacheese, okay, when I play online. And I'm going to talk about Settlers of Catan, the game, and the mathematics behind some of it. Maybe this will help many of you attain great heights and become grandmasters in the game. Not that that's necessarily the ultimate goal. My main thing is to have fun. So look, anyway, what I want to talk about is, for example, let's say a 7 rolls. So I'm going to talk to people who already know the game for the most part. So let's say a 7 rolls, and you have to move the robber, and maybe you're losing cards if you had 8 or more, right? Greater than 7 cards. And you're upset and you're frustrated, and you're like, well, why is it so unfair that 7 never rolls, or it rolled 3 times in a row, or maybe what about a 12? Why is it so unlikely, or a 2, right? Why is it so unlikely for a 2 or 12 to roll versus a 7, right? And why, for example, if somebody says, oh wow, a 12 rolled 5 times in a row, they're really upset, right? Or they think the game is some kind of somehow rigged, or it's cheating on you, or right, something like that. Well, let me tell you, I don't think anything is rigged and nothing is cheating. You know, any outcome is possible, no matter how unlikely, no matter how small the probability of it happening. Something has to happen. And actually every event, right, if it's specific and in the order that it's in, has exactly really the same likelihood of happening. Just something had to happen. But from the beginning, before something happens, when we predict it, it does seem very unlikely sometimes to have, let's say, you know, 10 twos in a row. Is it possible? Yeah, it's possible. Has it ever happened? Let's see, 136 to the 10th power? Oh, wow, that's very small. But I think maybe it possibly, I don't know, like 8 twos in a row. I'm pretty sure it did in the millions of games that have been played so far. Okay, anyway, let's move on. So, what is this idea, this notion of rolling a sum of die and it being a 2, a 3, a 4, right? The possible outcomes are from 2 to 12, right? You see the number, for example, let's take this number 5 right here. See that number 5? I'm circling that number, okay? That number 5, it has actually 4 dots below it on this little, this is a board game setup. Actually, in real life, you have these little circles, these tokens with 5 and little 4 production points is what it's called. And what these are, these 4, is actually telling you how likely something is to happen. The more you have of these production points, which I sometimes just ignore, but still understand what's going on here, right? The point of this is each production point is an outcome that's possible based on the die. For example, what if a 1 rolls, the minimum smallest number for a 1 on the 6-sided die, right? And what if a 1 rolls with a 4? Well, that works. What about a 2, but then a 3 needs to happen, right? Or maybe the other way around. Maybe a 3 happened first in the first die, and a 2 happened on the second. Or a 4 and a 1, right? And then these are the only combinations to get a 5 in the sum, right? Like if you have a 6 already, you can't get a -1. There's no die -1. Or a 5, you don't have a 0 on a die, right? So on our 6-sided die, we basically have the outcomes possible if you do 2 of them, with combinations of 1, 2, 3, right? All those from the 1 to 6 and 1 to 6. So the sums can be from between 2 and 12, but they're not equally likely, okay? Why is it the most likely that you have a 7 occurring? Well, a 7 occurring, actually, it's going to be 6 of these production points, okay? And the 6 and 8 are the ones that are non-robber ones that have 5 production points, okay? But let me show you, let's break this down as follows. So let's say you have the smallest numbers, so 1 and 1 roll, okay? Or maybe you have the first die being a 1, but the next one's a 2, or maybe a 1, 3, or a 1, 4, a 1, 5, a 1, 6. So these are 6 possibilities with just having the first die being a 1. And we'll have 36 such possibilities, because if a second die is a 2, a first die is a 2, right? The second one's going to be, again, a 1, a 2, and all the way to a 6, right? And this actually goes on and on with then 3. So let's actually write all this out. 3, 1. 3 could be, and then followed by 2. It could be that we have 3 followed by a 3, and that's going to be a sum of 6, right? And then we could have maybe a 3 and a 4, 3 and a 5 on the second die, and then 3 and a 6. And maybe, again, we could get 4, 1, 4, 2, right? 4, 3, 4, 4, 4, 5, and 4, 4, 6. That's going to be a 10. Here's a 6 if you get 5, 1, and a 7 if you get 5, 2. 5, 3 could happen, 5, 4 could happen. Each of these are equally likely, right? kind of by the symmetric argument or whatnot. We're using a uniform distribution on every outcome being equally likely. The way the dice are equally weighed. There's nothing like number one comes out more likely than number three, which it actually could in real life, right? There's obviously not completely perfect symmetry in the real world. Okay, so 5, 6, and then I'll do 6, 1, 6, 2, 6, 3, and let me show you where I'm going with this. 6, 4, and that's a 10, and then 6, 5, that's an 11, and 6, 6, that's the maximum 12. So you're wondering, well, how do I get a, let's say a 2? Well, the only way I get a 2 is from this, right here, this possibility of 1 and 1, right? And that's only one such. Or a 12, there's only one such, right? And you can do diagonals. Let me show you why. A 3 can happen either with this one, 1, 2, or the 2, 1, right? Or the 11 can happen with two possibilities with the 5, 6, and 6, 5, right? Then if you have a 4, think about that. The 4, right? It could be a 1, 3, 1 plus 3, or it could be a 2 plus 2, or it could be a 3 plus 1. And the 10 is symmetrically, it's the same, it's a counterpart to the 4 in the sense that it's going to be equally likely also to occur. So sometimes you're wondering, should I place it with the 10 or the 4? Really go for the resource type versus what's going to be more likely to happen. They're both equally likely. Now that doesn't mean that they're going to be both happening in the same amount over the game, right? Throughout the game. Actually, what will happen is maybe you have definitely probably will have more 4s and 10s or the other way around. And then, but don't think this is rigged or it's unfair. It's just something has to happen, right? Maybe you have all together like 30 10s. Right? Or like not 30 4s or 10s. So maybe you could have 15 15, but you could have had maybe 13 and 17. And you don't even know which one it would be, 10 or 4, right? So anyway, here's a way to get 10s. And then if you do a 5 or a 9, we talked about the 5, remember? 1, 4, 2, 3, 3, 2, and 4, 1. Remember we talked about those right here? See? That was the 5, that's why the 4 production points. And so we have that's possibility for the 5, those possibilities for the 5, this is possibilities for the 9. It's kind of cool that you can do diagonal little treatment like this, right? Just one way to see it. And then the 6 can happen with 1, 2, 3, 4, 5 possibilities, or so the chance basically of a 6 happening is 5 over 36, 5/36, right? And 8 also the most common one that's not a 7 is going to be 5 possibilities. And finally the 7 right here, right? That's 7, the robber number, right? The kind of the bad, scary number is this one. And there's maximum, it's the most common one because there are 6 such things. So probability of a 7 occurring, or some, let's say 7 some, is equal to 6 over 36, which is equal to a 1 over 36 if you simplify it, which is approximately what? 16 2/3, so 16.6%, right? And you can put a little bar over it to get it exact. Okay. So now, what is a question that people sometimes ask? They wonder, well, should I hold my cards? Let's say you have 8 or more cards in the base game of 4-player. For example, that's kind of what I'm more alluding to here. This little treatment here done in this video. Okay, so well, let's assume we're not playing Cities and Knights. We're just playing a base Catan game with 4 players. It could be 6, could be 5, could be 3 also. We're going to play this basically with 4 players, kind of just the general, more common game, I think, style. So look at this. What's the chance that, let's say you pass your turn and it comes back to you without a 7 rolling and four rolls, right? So probability that no 7 in 4 rolls, right, occurs. Right? What happens? Well, what you do is you say, well, no 7 occurring is 1 minus a 5, 6 that it, no 7 occurring, what is that? Well, a 7 occurring is 5, 6, right? So a no 7 occurring, 6 over 1, 6, right? So a no 7 occurring is 1 minus a 6 or 5, 6, right? And then if you take it to the 4th power, because you're doing 4 rolls, okay, so you multiply that by itself 4 times. In other words, we're talking about 5 over 6, right? 5, 6 to the 4th power, which is, if you do the math, it's 5, 5, 5, 5. 25 squared is 625 over a 36 squared, 1,296, okay? You're wondering, well, what's the chance that no 6 occurs? And let's see, if we calculate it, let's see, approximate it, that's a little bit less, that's a 48% about, a little less than 50%, okay, 48 something percent, okay? So actually, you have some kind of likelihood that if, you have about half, approximately half, right? Approximately half chance that you will actually get back your turn without a 7 rolling. And somebody may wonder, well, what's the chance that a 7 will roll at least once? 7 rolls in next 4 turns, right? And what's the chance of that? Well, you may want to go directly, like, oh, a 7 happens and then 7 doesn't. Or maybe a 7 does not happen and then it happens, and then it happens again and then it doesn't. But there's so many ways to go directly about this, actually 15, because think about it, yes or no, yes or no, yes or no, yes or no in the 4 turns, that's 2 to the 4th power, 16. So the 7 not occurring, no, 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 is just one thing you have to look at, one case. Imagine you have 15 cases to look at directly going, like here's a 7 here or there. So what I would recommend doing here is saying, look, a 7 rolls the next 4 turns and the 7 actually does roll. It's the same thing as 100% or 1 minus it not rolling, right? So it's 1 minus that, what is it, 5, 6 to the 4th power, which we calculated it to be 625 over 1296. And so this is approximately then what? 52%, right? So more than likely, it will roll, but barely, also approximately 1/2, right? Approximately 1/2 chance. Cool, right? So if you're wondering, should I give away a 3 cards for 1 to a really good player just because I'm worried about losing on a 7? First of all, remember, even after a turn, maybe you will pick up to 8 cards, and then you just have, of course, less chance of getting the 7 happening on your turn. But like we'll take it to the 3rd power, this no 7 occurs thing and not the 4th. But in general, right? Be careful with just randomly trading away because you're so scared of the 7. Okay, that's my gameplay, is that I usually don't shy away from the 7 occurring all the time. Okay, but again, anything's possible, right? So in fact, more than 50% chance that it will occur, and so you have to be watching out, right? So I just wanted to show you how you can quickly compute these numbers so you can understand what makes some course of action, and what do you do, right? Okay, now let's do some other few other things. So for example, let's say we are right, we have our spot right, I don't know, some spot right here. We have some good good wheat production right here. To see that 6, 4, 11, 6 wheat, 4 wheat, 11 sheep, and maybe we have this spot here, the 10 brick, 3 wood, and 8 ore, right? And you're wondering, well, let's say I begin with, or let's keep it. There's so many questions you can answer, and you can basically answer almost any one of them. Let's just let's start with a question of saying, let's see, what's the chance that I will get a sheep, or not a sheep? Let's do this. What is the chance that I will get an ore or a wheat? So probability of ore or wheat given the 2 red spots above, let's say. So we kind of, not just making things up. So that's going to be, well, think about it. Or wheat given red 2 spots above, and then maybe even more involved. Let's do this. In the next 2 turns. In next 2 turns. And let's actually say, make it a little easier, ore and wheat. So we want to get 1 ore and we want to get 1 wheat, right? So that's we can't get more. We don't have a city or anything. We're just going to imagine we have a settlement, right? So here's what you do. You can say, well, maybe I'll have an ore, probability of ore on the first, and then probability, so times, because that's what you do in probability when you really have the outcomes in that order. You times probability of maybe the wheat on the second, okay? But you can also reverse it, right? So then plus and then basically you maybe have first ore happening. First wheat coming out first, and then just kind of random example of what you can do. Like let's say you're interested in, in 2 turns, will I have another extra wheat and ore? What's the chance, right? Let's see. And then probability wheat, then ore, then the second, right? in the second roll. You get a or in the second roll. So what is that equal to? Well, that's equal to probability of or first. All right. Or we have actually 5 production points. It's an 8, right? Right here. That's the only or we can possibly get with having these 2 settlements initially. And so we have, okay, 536, right? 536. That's what the chance of 8 occurring would be. And then wheat, what is the chance of wheat happening? Well, it's not only a 6 occurring for wheat, you'd also have a 4, and those possibilities can be the 5 possibilities for the 6 or the 3 possibilities for the what? For the 4. That's 8 possibilities out of 36, right? 8 possibilities out of 36 possible. And then we can obviously reverse it the same way, so you can just multiply that by a 2. Okay? And that's going to equal to what? Let's just do this. So it's what? 2, so 5 times, I'm going to prime factorize everything. 2, 2, 2, that's the 8, right? 2, 2, 2, and then times another 2 on the top. And on the bottom, we have 36, which is a 2. I like to prime factorize numbers. It's a 2, 2, 3, 3, right? And then another, that's what, a 6 times a 6, and another 2, 2, 2, 3, 3, right? Just a way to kind of simplify numbers and then to work with that. Now you don't have to, you can just right away see what happens. But the 2's cancel, the prime factors cancel, 2, 2, 2. You have 3 2's cancel on the top, and then we have what, 10 remaining on the top, and on the bottom we have 3, 3, 3, 3. That's 81 times a 2, which is a 162, okay? That's what it is, and that's going to be approximately 1 over 16-ish, right? 16th. 1/16 is what? That's approximately 0.0625-ish. So 0.06, about 6% I'm getting, okay? Okay. So that's very unlikely, right? But that you're going to get an or and a wheat or a wheat and an or. But so like, if you're thinking, well, I need those to get a city in that specific order, I mean, wheat and or and wheat, guess what? More than likely, it's not happening in 2 rolls. Okay, if you start adding more rolls, yeah, more likelihood that it will happen. Okay, so cool, right? Okay. Well, so next I want to tell you this. Sometimes people complain, I've seen it on like Facebook or chats, whatever. They're like, well, look, I have this outcome. Here are the dice rolls, right? And what's weird, what's wrong with that is they may wonder, well, you know, it's the dice. This is so unfair. This is rigged. This game is not, you know, this distribution Catan is doing is just wrong, right? Guess what? Anything is possible, and some outcome has to happen. And if you don't like it, well, it's, you know, it doesn't mean it's wrong and it's impossible. Okay, so that's what my defense will be for anything like that. Let me show you. I wrote a little simulation in MATLAB. Okay, where let me kind of, if you want to copy this here, you kind of pause the video and copy this. Okay, but what happens is, look, I'm saying I take this kind of statistical average of Catan's. Typically, if you have a 4-player game, a base game, you will have on average 80 average rolls until the game ends. Okay, so about 20, 20, 20, 20 per person. Okay, so, and I said, look, let's get a standard deviation of about 30. Okay, standard deviation, STD. Okay, and I did that because every time when I'm doing this, as I simulate a run, is I'm saying, hey, there are going to be n runs, okay, like however many games, like 25 games or whatever. Actually, yeah, and so, actually, no, n is at 12, right, because it's just going to be, what is it, how many possibilities there are, right? So anyway, I'm going to say, yeah, so I'm saying this. I'm going to say, look, here's how many actually is going to happen, okay? Yeah, it's end game. So how many we're actually going to have each game? So maybe one game you'll have the ending in 60 turns instead of 80. Another game in 85, right? Another game in 90. Maybe a game quickly ends at like 42, right? So we don't know, but it's approximately around the standard distribution like that, right? Gaussian distribution, where more than likely it's an 80, but maybe it could be 70 or 60, very less, you know, less likely, or even maybe a little 30. I mean, I'm kind of assuming even a 1 can happen, right? Which is not, you know, that we can't win with a 1 because that's not going to change any amount of points. But in general, that's how it functions. And so here we are. We get, and then this, as it runs, every game you play, right, what happens is this. I say, look, here are the outcomes, the weights of the outcomes, right? The 136, the 236, basically for each of those dice sum rolls. And so then I say, like, let's say we have however many games, right? So then these games are played, and we'll plug in different games, everyone. So, and then what happens is, look, I'm going to show you two things. One is the just normal distribution for that specific how many games you would have based on what we are expecting kind of statistically, and then the normal distribution being kind of typically the one that happens in life. In life, a lot of things go by that normal distribution if they're just randomly occurring in real life. It's a very strong, powerful tool to just know that Gaussian distribution, the normal distribution with the standard deviation and that mean that you're around, right? The center, the mean that you're around. So the average value. Anyway, so look, what I did here is I say, well, look, here's just, let's say we play one game. And what happened is maybe the 2 rolled, here it says 3 times, right? That's a 3 right there. That's a 3. And then maybe a 3 rolled all the way to 6 times. And a 4 rolled in 18 times versus a 10 only rolling 6, right? So you may think, well, that's unfair. Well, it's what it is. So a person with a 4 instead of the 6, having chosen that from the beginning, more than likely had a big advantage, right? But the 7 rolled the most, we probably expected that, and then the 8 rolled a lot, the 6 rolled less, right? So that's what it is. And then this red one is kind of just what you would expect. And we're just wondering, does it approach, the red one, does it really approach? I mean, is it approached by the black, the kind of as it goes on with more games going on? And so look, if I run 2 games, here's what happens. The black one gets a little closer to the red one, right? It seems like. And so I'm just saying, here are more rolls, and here's what happened. And I'm distributing them in a histogram, basically. Anyway, but not plotting it differently than a histogram. And then look, here's 5 games. So this is what, 1 game? And then what after 2 games, what happens? And then what happens after 5 games? And what's interesting actually to me, I'll tell you after just running the simulation, is that look, after 25 games here, and you can do more, you just kind of, the simulation, you can try it out actually, look. Try it. I'm going to pause it again. You can just kind of copy this if you like and code in MATLAB or even Octave, or I think Python does very similar, or R code, okay? But a slightly different code, of course, for that, the syntax. Anyway, so this MATLAB code, what happens is it finally generates, and this is a moving graph. You can see the stuff building on its own in time. What you see, this interesting thing is, look, the black curve, it does approach some shape, but it's not exactly, it's not at all that Gaussian, right? Kind of cool, right? So it's a little different, and I would expect it to be closer than that. So more than likely, you have these smaller numbers occurring a little more than you would expect by Gaussian normal distribution, which is going to make sense. So the Catan the distribution of dice rolls is a little different, okay, turning out to be than our the normal distribution, which is interesting. It's a little surprising to me, but that's what it is. And we could actually maybe have a little distribution for that to find out what exactly it is, a little theory behind it to fill it out. So I just want to show you a few interesting concepts behind the Settlers of Catan. Hope you like it, and I'll maybe do a few more videos later on with some more detailed examples. All right, everyone have a wonderful day, and I'll talk to you later. Bye.